Here's a generic picture of the electrocyclic rearrangement reactions. We're going to classify the system according to the size of the pi system. How many pi electrons are involved? We'll call it a k pi electron system, and in the electrocyclic ring closing reaction, we'll take that linear pi system and the terminal positions alpha and omega and make a new sigma bond there. The resulting molecule will have k-2 pi electrons because 2 of the pi electrons went into making the new sigma bond. In the electrocyclic ring opening reaction, we're just going to do the reverse process. A k-2 pi electron cyclic system will end up becoming a linear k pi electron system because the 2 electrons from the sigma bond will now join the pi system. In the electrocyclic ring closure reaction, we're taking a planar pi system of sp2 hybridized atoms and we're transforming it into a ring system which has undergone rehybridization at the termini to introduce 2 new sp3 centers. If there are sufficient substituent differences on these positions, we'll create new stereocenters at these sp3 atoms. The stereochemistry at these positions is determined by the double bond geometry at the terminal positions of the linear pi system. These reactions are stereospecific, and we'll learn that the stereochemical preferences are dependent upon the frontier molecular orbitals that are involved in the process. The electrocyclic reactions go by 2 pathways, and these pathways are defined by the motion or trajectories of the atoms in the terminal position. Specifically, we're looking at how these atoms twist during either the electrocyclic ring closure or in the reverse process, electrocyclic ring opening. One pathway is known as the conrotatory process, and in this case, the terminal positions twist both in the same direction, either clockwise or counterclockwise. So, for example, in the case of ring closure, we're taking this planar system and we're twisting both ends in the clockwise direction. That'll take this capital A and move it above the plane for this terminal position, alpha, and it'll take the capital Z and move it above the plane for the terminal position, omega. That'll produce the stereoisomer here, in which the capital letters are both on the same side of the plane. Let's take a look at the ring closure reaction for the conrotatory process. Here the ends are going to twist again in the same direction. The example that's shown shows them twisting in the counterclockwise direction. That'll take the 2 atoms that are above the plane and lay them down so that the A is going to be on the outside of this linear pi system, while the Z lays down into the inner part of this pi system. Disrotatory process is the case where the twisting goes in opposite direction. One end will twist clockwise and the other end will twist counterclockwise. So here we have the alpha end twisting in the counterclockwise direction. That's going to take the capital A and place it below the plane. The omega end is twisting in the clockwise direction to take the capital Z and place it above the plane. On ring opening, the process is just reverse. The omega end is twisting in the counterclockwise direction. That's going to take the Z and place it on the inner part of that pi system. And the alpha end is twisting in the clockwise direction, and that's going to take the capital A and move it to the outside of the pi system. That's the disrotatory ring opening reaction. Your notes are hyperlinked to JMOL animation of these reaction pathways. Here we're looking at the disrotatory ring closure process, and since these are JMOLs, you can go ahead and rotate them to get you an orientation that's suitable for viewing the twisting motion. In the disrotatory process, you're going to notice that the hydrogen atom on the left twists in the counterclockwise direction. The hydrogen atom on the right is going to twist in the clockwise direction, and you'll see the cis isomer emerge from this animation. Here's the transition state. You can begin to see the cis isomer develop. If we continue the process, at the end of the reaction, you can see that the cis isomer is forming. The new single bond will be formed right there. The examples shown here illustrate that electrocyclic reactions are stereospecific. The top case has to do with electrocyclic ring opening reactions for a 4 pi electron system. Remember, that's looking at the product, the linear pi system. So in the ring opening case, we start with this cyclobutene, and if we start with the cis isomer, we generate the Ze isomer. You should convince yourself that that's a conrotatory ring opening process. The cis ring system generates the Ze double bond geometries. The trans ring system generates the EE double bond geometries. And so for that reason, we know these reactions are stereospecific. On the bottom, we're illustrating electrocyclic ring closure reactions for a K is equal to 6 pi electron system. In the first case, the terminal double bonds both have E geometry. This process, as we'll learn, is a disrotatory process, and you should convince yourself that the disrotatory process, twisting in the opposite directions, is going to generate the cis isomer. The EE configuration, by disrotatory process, generates the cis isomer. The Ze double bond configuration, by the disrotatory process, generates the trans isomer. Again, we know that this is a stereospecific process because the product stereochemistry, trans or cis, is determined by the stereochemistry of the starting materials, Ez or EE. In the next webcast, we want to understand why the 4 pi electron system goes by a conrotatory process and why the 6 pi electron system goes by a disrotatory process.